Let's take a look at another example. Let's solve y double prime plus 9y equals 1/4 cosecant of 3x using variation of parameters. So this is still section 4.6. We start out as we always do. Step 1 is going to be to solve the homogeneous differential equation. So we're going to find our complementary solution. In this case, we have y double prime plus 9y equal to 0. The auxiliary equation would be m squared plus 9 equals to 0. We can solve this by taking the 9 to the other side, taking the square root, and that's going to produce plus or minus 3i. So we get a complex solution, so the form alpha plus or minus beta I, and therefore the complementary solution is going to be c1 cosine of 3x plus c2 sine of 3x. And then the functions we're going to need to use in a moment, we can call the y1, the first part of this, the first unique part of our complementary solution. This is cosine 3x. And then over here, this will be our y2. y2 will be equal to sine 3x. So step 1, that's done. Step 2 is we now want to find the particular solution. Let's find y sub p. We know that y sub p is going to have the following form. So y sub p is going to be equal to u1 y1 plus u2 y2. That is, it's going to look like u1 times the cosine of 3x plus u2 times the sine of 3x. We have our formulas for u1 prime and u2 prime. We know that u1 prime, this is going to be equal to negative y2 times f of x divided by the Wronskian. Oops. And u2 prime is going to be equal to positive y1 times f of x divided by the Wronskian, where f of x for this differential equation is 1/4 cosecant of 3x. Okay. So let's go ahead and compute the Wronskian first. The Wronskian we know is the determinant of y1 prime with y2 prime. We have our y1 and our y2. Let's come down here and compute their derivatives. This one will end up being a negative 3 sine 3x. y2 prime will be a 3 cosine 3x. So our Wronskian looks like this. It's going to be cosine 3x negative 3 sine 3x sine 3x 3 cosine 3x. We multiply the diagonals, so we are going to get a 3 cosine times cosine is cosine squared 3x. Be careful with your sign here. When we do the determinant, it's a subtraction, but then we have sine 3x times negative 3 sine 3x, which will give us a negative 3 sine squared 3x. So this is equal to 3 cosine squared 3x plus 3 sine squared 3x. We can go ahead and factor out the 3, and we're left with probably one of the most famous trig identities. This is the Pythagorean identity for sine and cosine. But cosine squared plus sine squared of an angle, that's equal to 1. So it turned out that the value of our Wronskian is simply going to be equal to 3. Sorry about that, bump the power button. We're back. So we computed the Wronskian and we get the value 3. So just to save some space, let me kind of erase this. So the Wronskian is equal to 3. And now we should be able to find u1 and u2. So u1 prime, this is equal to negative y2, which is going to be negative sine 3x times f of x, which is 1/4 cosecant 3x, all divided by the Wronskian, which is 3. Therefore, we're going to get that u1 prime is going to be equal to, if we look at these coefficients here, we have a negative, a 1/4, and a 3. Negative 1/4 divided by 3 would give us negative 1/12. But because sine and cosecant are reciprocals, cosecant is the same thing as 1 over sine. So sine 3x times 1 over sine 3x, that cancels as a factor of 1. And so u1 prime is simply equal to negative 1/12. We can find u1 by then integrating both sides of this with respect to x. The antiderivative and the derivative cancel, and so we find that u1 is equal to negative 1/12 x. And again, don't worry about the concept of integration on this. I'll explain in a minute why we don't need to concern ourselves with that. But we now have u1. Let's go ahead and solve for u2. So u2 prime, this is equal to y1. y1 from over here is the cosine of 3x times f of x, which is 1/4 cosecant 3x, all divided by the Wronskian w, which we said had the value 3. The 1/4 divided by 3 will again give us 1/12, and it might be helpful to think of the cosecant as like 1 over the sine. And so we end up getting 1/12 cosine 3x over sine 3x, which you could even change into cotangent if you wanted to. But if you're doing the integration by hand on this, which we're about to do in a second, you actually would want to leave it like this because it would be like a u sub. So to find u2, we now integrate. We're going to integrate both sides with respect to x. You can pull the constant out, pull that 1/12 out. Cosine 3x divided by sine 3x dx. Again, if you made it cotangent, you can just use a table for integration. I'm fine with that. But if you wanted to do it out by hand, we already are using u, so let's do w substitution. Let w equal the denominator. That would be sine 3x. And then dw would be 3 cosine 3x. So we would need to put a multiplication by 3 on the inside to fit the substitution by putting a division by 3 on the outside. So we're going to get a 1 over 36 for this factor. This would now become the integral of 1 over w dw. That's going to be 1 over 36, the natural log of the absolute value of w, which is 1 over 36, the natural log of the sine of 3x. And that would be our u2. So 1, so 1 over 36, the ln of the absolute value of the sine of 3x. That would be our u2. And now let's just kind of go ahead. Let's wrap it all up. Let's put everything together. We already found our complementary solution. We now have the coefficients, if you will, to find the particular solution. So we can go ahead and summarize this. Maybe if the computer wants to work. Come on. So our general solution y is going to be equal to yc, which if you look back through it, yc was c1 cosine 3x plus c2 sine 3x plus u1, which is negative 1/2 x not negative 1/2, negative 1/12 x times y1, which was the cosine of 3x, and then plus u2, which is 1/36 the ln, the absolute value of the sine of 3x times y2, where y2 was the sine of 3x. And so this would be our general solution. So we've gone ahead and we've actually solved for this differential equation.